Hey guys, welcome to section 8.1 on analysis of variance. Hope you had a good time getting started on the lab and that you've made your way through that to kind of get the sense of the connections between analysis of variance and what we're going to be doing, or what we have been doing. Now in this section we're going to take a look at a particular experiment or a case study to understand some of the ideas of analysis of variance. I'm going to walk you through some of the intuition, the big ideas of analysis of variance. And in section 8.2 we'll look at some of the follow-up tests that are often carried out once we've conducted the initial procedure of the ANOVA. Now I'm going a little bit out of order here. I just want to introduce the basic idea of this experiment, try to motivate the procedures that we're going to carry out. Now this is on RStudio. You'll have the file that will look at this data, and it's an experiment, so let's take a look. All right, this was a study on the effect of restricting caloric intake on life expectancy, and it was carried out in female mice. They were randomly assigned to one of 6 treatment groups. And these are identified by letters and numbers. So NP refers to the unlimited, non-purified standard diet for laboratory mice. I guess that would be sort of the unlimited buffet, not necessarily to be desired. NN85, control group, was fed normally both before and after weaning. The caloric intake was controlled at 85 kilocalories per week after weaning. So that was the control group. Then some of the manipulations, there were manipulations before and after weaning. Well, actually after weaning. So NR50 was the normal diet before weaning and reduced calorie diet of 50 kilocalories per week after weaning. There was the RR50, yes, it was before weaning, so reduced calorie diet of 50 kilocalories per week before and after weaning. Then NR50, low pro, normal diet before weaning, restricted diet of 50 kcals per week after weaning with dietary protein content decreased with advancing age. And NR40, formal diet before weaning, severely reduced calorie diet of 50 kilocalories per week after weaning, and there were several questions of interest to be addressed. But first let me give you the reference for this study. This is from the Journal of Nutrition 1986, and the authors are given the subtitle of the study was The Retardation of Aging in Mice by Dietary Restriction, Longevity, Cancer Immunity, and Lifetime Energy Intake, in case you want to follow up on that. All right, here are the questions or the considerations, the planned comparisons among the groups in the diet restriction study. So they were curious whether reducing from 85 to 50 kilocalories per week would increase lifespan. So to answer that, they would have to make this comparison between these two groups. For B, is there an effect of pre-weaning diet restriction? So comparing the NR50 with the RR50. Third, does further reduction from 50 to 40 after weaning increase lifespan even more? So sort of is there a dose-response relationship to reducing caloric intake post-weaning? Then comparison, does reduction in protein with same calories change lifetime distribution? So reducing the number of reducing amount of protein. That's D. Then finally E, do control mice have the same lifetimes as laboratory mice? So they wanted to make sure to compare the NN85 control with the kind of unlimited non-purified diet. All right. So that's the layout. Now I want to go back to the beginning and we'll look at how we're going to approach that. So using the analysis of variance, the challenge is that we have several groups to compare. We don't just have a pairwise comparison of 2 like we were looking at in chapter 6, so there's a little bit more involved. We have the basic ANOVA and the ANOVA model to take a look at. Now I think this quote from a textbook that I used to use for this class does a good idea of capturing the basics of ANOVA. When we ask if a set of sample means gives evidence for differences among the population means, what matters is not how far apart the sample means are, but how far apart they are relative to the variability of individual observations. Okay, so what you should have in mind when you think about that is the following. Let's go back to the applet that I showed you last time. I still have the link here under the section 8.1 lesson. And that's a one-way ANOVA idea. So we've got these differences in the means between three groups. Right? Sample sizes were 20, and there's some standard deviation that looks to be around 2 or so. Now, here's a difference. This difference is sort of strongly, well, not strong, the p-value is relatively small. But now if we take this same difference, but we let there be more variability within the groups by increasing the standard deviation, then that same difference doesn't seem to be so important anymore because there's so much variability overall, right? We can make that even bigger and arbitrarily big by increasing the variability. Then this variability between or sometimes among the groups doesn't matter. But then if we shrink the variability so the groups are homogeneous, and those same differences in means start to look really important, and in fact we end up getting a very small p-value in that case. So that's the idea of what this quote means. The variability relative to the variability, how far apart the means are relative to the variability of individual observations. So we call it the analysis of variance, but really it's an analysis of means, but the way we do it, the sort of mechanism by which we say something about the difference in means is by looking at how the variability between or among the means differs from the variability within the groups that we're comparing. All right, another way to think about this from our textbook is the basic idea is to compare measures of variability both between the groups and within each group as a way to assess how different the groups really are. Okay, then let's take a look at this diagram of what's going on. We're going to consider, this numbering scheme is kind of arbitrary. I tried to be consistent with the setup of the textbook. Before we were thinking about sampling either two independent populations, could have been from an observational study or could have been from an experiment. But that was when we were doing comparisons of two groups in chapter 6 and even earlier back in chapters 3 and 4. We've also looked at matched pairs setups where each observation was a pair. Here we're thinking of individual populations, sort of like with the two-sample t-test or two-sample comparison of proportions. But now instead of 2, we have k, meaning some arbitrary number, not too large, but a relatively limited number of populations that we want to compare. So we could define the means mu1 through mu k of the populations. Now we're going to assume that all the standard deviations are the same, and that's a strong assumption we'll need to check when we carry out a standard deviation and carry out an analysis of variance. Now when I teach stats 2, I talk about other alternatives here, that is transforming the data to make the standard deviations conform. Perhaps they're different on the original scale, but if we convert to a log scale, then we find this condition holds. So we can deal with it if that's violated, but initially, to proceed with the raw data as is, we need to check that condition. So correspondingly, we have sample means x1 through xk and associated standard deviations s1 through sk. So the conditions for applying ANOVA are these. We have k independent, simple random samples, one from each of k populations. That's not k-pop, that's k populations for the BTS fans in the audience. Now I should note that the populations may be virtual populations. When we have an experiment, we're sort of creating a virtual population by means of assigning some people to get new drug A and others to get new drug B and others to get the existing drug or a placebo. Right? Those are populations that didn't exist until we started the experiment. And on the other hand, if we're doing an observational study, a longitudinal study, like a national health study, then we probably do have existing populations and we're comparing groups. Okay? So, 2, each of the K populations has a normal distribution with an unknown mean. So we're assuming normality. If the sample sizes are large, that normality assumption is not going to be nearly as important because the central limit theorem that we learned about earlier in the course will mean that the sampling distribution of the mean is still going to be normal, so we'd be okay. But it is a condition that we're thinking about. And 3rd, all the populations have the same standard deviation, which is what I had mentioned, but that's unknown. All right, so here's the case that I had already introduced to you, and that's what we're going to consider. Now we're going to use R to create plots to explore the possibility of differences among the means. So how should we go about doing that? Well, we ought to get the data first, and then just kind of take a look at it. So why don't you come with me into the cloud? I've got a link over here. Let's make sure that it takes us to the right place. I'm going to close that. Click on this to RStudio Cloud, and let's hope that it's there where it's supposed to be. You never can tell about these RMD files. Okay, we're open. Let's go ahead and open this mice diet analysis. That's the RMD file. Oh, I'm going to restart and clear that output. Now I've got the PDF, or I've got the RMD with the ANOVA commands here as well for reference in Chapter 8. It was also in your folder, or workspace for the lab that I asked you to do first. Okay, so this should hopefully be kind of straightforward now that you've done the lab. But the first step is to read in the data. So I'm going to go read that in. Now I'll make a brief comment here on the fig width, fig height setting. This is a default setting for the whole document. Separately, when talking about the project, I made a short video talking about how to set the width and the height. I focused on setting the height, but you could set the width as well for a plot or a chunk of output, figure output that you get from R. So keep that in mind. The others are kind of nothing new. They're just to kind of suppress a lot of messages that you don't want showing up in your document. All right, then let's take a look at the plot. So, well, sorry, this is not the plot. This is some summary statistics, but the plot is what I suggested we look at. Either a histogram. You can imagine this being a dot plot too, with lots of dots. All right, let's see. Actually, I think what you'll notice is we can do pretty well by replacing that. Now we'd probably want to reduce the dot size. So let me undo this, and I'll give you one more version of this. Because I wouldn't usually use the dot plot here because we have a pretty large sample size in each group. But just so that you have it for reference, I'm going to make it 10% because that is a large sample. All right, so that shows you the detailed data. But for this data, I like the histogram. I think we see some skewness in the data in terms of lifetimes. For some of the groups, we see variability. We see clustering at certain values, and probably most simply is to just look at the box plot for comparing, because then we can see the medians of the groups as well as the shape because of the tail and the kind of dribbling little mice droppings below the box plots. Perhaps those are some values with fairly small lifetimes. But notice the sample sizes are, and for all groups, I guess the lowest sample size was 41, up to a maximum of 71. So we've got a pretty good overall sample size. While we're here, why don't we just get that overall sample size? What can we do? Can we do dim of mice? That's not too bad. 349 rows and 2 columns. What are the 2 columns? Well, we could do head of mice or glimpse of mice. See that it's lifetime and diet. And maybe while I'm here, just to give a little bit more, this is not really summary statistics, so it doesn't quite fit there. But remember that that's a way to get the sense of what it looks like. But short of that, then you probably want to use view. I use the comment just because I don't want it to run when I knit, because R doesn't know what to do with interactive sorts of procedures. But if you want to have access to that, you can scroll through. I think I've highlighted before this idea of either sorting or filtering. You could pick certain ones to filter on. Could we do like RR50 and do that? Sure we could, and then we would just get those. So lots of things you can do, just kind of exploring that data. But let's get rid of that and get back on track. All right, so we had a look at the data. Now let's pick up with where we left off. We use R to create plots to explore the possibility of differences among the means. So I like a box plot here for doing that. Dot plot for smaller samples, sample sizes would be fine. And this certainly suggests to me some, what do I want to say, systematic variability in the lifetimes. It doesn't seem to be explained just by the general variability. That is, that variability between is looking kind of big compared to the variability within. If you like, maybe you can look at the histograms and also see that variability between, there is a fair amount of variability within, but still the shifting over here suggests maybe a treatment effect. All right, so let's carry on then. So the big picture of ANOVA is just that. Is the variability across populations greater than the variability within populations? Or we could think of it as variability between versus within, among versus within, lots of different terminology used. So I don't want you to be tied to just one specific term there. Hypothesis test here. Now let's be careful, because our hypothesis test is going to look a bit different now. Our null is mu1 equals mu2 equals mu k. It's very specific. The alternative, we cannot have a one-sided hypothesis within ANOVA, at least for a global alternative hypothesis. All we can say is at least one of these things is not like the other. Short musical interlude here.
One of these things, one of these things doesn't belong. Can you tell which thing is not like the other by the time I finish this song?
See how the box plots just move down lower, and here we've got the variability. So it looks like Sesame Street knew a little bit about statistics too. All right, so let's get back on track here. At least one of these things is not like the other, seems to be the theme here. So our test statistic is the ratio of the variability among the group over the variability within. We just have to think about how we're going to measure variability. So it really becomes an accounting problem. And if you have a chance to take accounting somewhere in college or afterwards, found that's one of those really useful life skills to have. You don't need it for these calculations, actually. But I think you'll appreciate them anyway. So, variation among the sample means versus variation among individuals in the same sample is what we're comparing. So this is a new test statistic, a new distribution. We've seen the Z, we've seen the T. If you've done genetics, you've seen the chi-square. It's not chi-square, it's chi-square because chi is T, and well, that's different. Anyway, so large test statistic is evidence against null. We're going to have to talk about this test statistic a little bit, though, and how we could use it to get p-values. So results are then summarized in the ANOVA table, and we'll learn about that and how we use that to present the results. But let's get to know some of the notation first that comes up in this. And it can just be an overabundance of notation. So you can find yourself drowning in symbols if you're not careful. So I'm going to try to walk a kind of middle ground here and introduce you to some specifics that come up later in this section. But don't lose sight of the big picture, which is a comparison of between and within, and the fact that p-values are still p-values. Lower p-values are going to be evidence against the null hypothesis, check conditions, all that. So k is the number of groups. N sub I is the sample size for each group. Sample mean for the groups, group 1 through group 6. Standard deviations for each group's total sample size. We get N by adding up all the individual sample sizes. And we can think about an overall mean either by adding up all the observations and dividing by n, or we can also think of it as a weighted average, really. If you think about it, you've got an ni over n. It's the fraction of the overall sample that's accounted for by group I really being multiplied by the group I mean. But however you look at it, it's an overall mean of all of the entire sample. So we're going to use this idea to apportion our variability. Our total variability is going to be called the total sum of squares, and we'll see what we mean by the sum of squares. Variability between the groups and variability within the groups. So the variability within is what we'll start with first. That's the amount of kind of noise or heterogeneity within each group, and here's the way we measure it. Well, standard deviation itself does a good job of measuring the variability within a particular group. So if we want the total variability within groups summed over all the groups, we're going to do that, but we're going to do it kind of in a very special way. Rather than just adding up the standard deviations, we're going to use the weights as the degrees of freedom. When we add those up, turns out the real reason for doing that is S1 squared has n minus 1 down below. So when we do that, what we're really going to be doing is adding up all the squared deviations within each group around the mean. Why squared deviations? Well, it really comes down to big ideas in mathematics like the Pythagorean theorem, that it's just easier to work with squares than on the original scale, just like the fact that the sides of a triangle don't sum to the hypotenuse. We have to square them and take the square root. Okay, so let's refer to our output. I'm going to set that up here. Okay, here we go. So we've got the standard deviations for each group here, and we've got the sample sizes. So in fact, we've got the associated degrees of freedom. So let me write down the first couple terms of the calculation, just so that you know what you're going to be doing, and then I'll let you go ahead and finish that off. So 56 minus 1 is the first degrees of freedom. So 56 minus 1 times, I think it was 6.99 squared. And now we're going to go down the line for each of these, take the degrees of freedom times the standard deviation squared. So if I just kind of put and so on dots here, then we would end up with 56 minus 1, because those happen to be the same sample sizes just by chance, times the associated standard deviation squared, which for this group was 6.68 squared. So that one happened to be close. So those two groups are quite close in a couple different ways. But when we add all those together, we get 15,297.4 as our total sum of squared errors. All right, then on the degrees of freedom front, we're just going to add up the degrees of freedom for each group. So the degrees of freedom within each sample is the sum of the degrees of freedom for each sample. So we've seen the n-1 degrees of freedom idea in the one sample t interval and hypothesis test. And so it comes up again here. We're just going to add up the degrees of freedom. And so it turns out that's a good way to deal with them. And we get n minus k overall. So you can think of that as the total sample size minus the number of groups, right? Because n is the total sample size, k groups. So in this case, what we're going to be getting is 56 minus 1 plus, turns out 57 minus 1. And so on up to 56 minus 1. And we get 349 minus 6. So it's 343 is the total degrees of freedom. And let's see, we saw over here when we did dimensions, we got 349 and 2. So that 349 minus 6 comes back here. All right, so that's our degrees of freedom for the within sum of squares. Now we're also going to get a degrees of freedom for the between, so stay tuned for that. Okay, there we go. Okay, so mean square error within groups. So what we're going to do is kind of adjust out by the degrees of freedom. So what we're going to try to do is set up a situation. So under the null hypothesis, the variability as measured by the mean square should be the same whether you're looking at within or between groups. And the way we do that is to take that sum of squared errors and divide by the degrees of freedom. That is the corresponding degrees of freedom. So we take that weighted average, and then we divide through by n minus k. So we already did the subcalculations for that. We had 15,297.4 divided by 343, and we get 44.6. Now it's more useful and more kind of sensible to think about the square root of that on the standard scale. That is not standard scale, but the original scale, because this has been squared. So if we're thinking about lifetime in days, then it would be days squared. So now we take the square root of this. So and then we're going to be on the original scale, and we can kind of make some sense of it. So 44.6, take the square root of that, we get 6.68. So that's useful because we remember back to the beginning of the course. Sorry, didn't mean to do that. In the beginning of the course, we talked about the 95% rule. So we could say, think about applying that to something like this. So maybe the mean is somewhere a little bit below the median. And if we took that 6.68, so almost 7, doubled it, we get close to 14, either side of the mean. So that's a spread of, well, if we just took maybe 4 times this, so 4 times 6.5-ish, well, let's just do it. 4 times 6.68, we get 26.7. Let's round up to 27, and think about that being the range of 95% of the data. Well, that doesn't do too badly, right? 27, the range here was about, something close to that. And you can look at the scale along here and see that 27 for a range of 4 standard deviations seems reasonable to encompass about 95% of the data. And also thinking about the conditions, the standard deviations don't vary a whole lot between the groups, a little bit here and there, but not enough really to invalidate our assumption. So that seems reasonable. Okay, so that's our standard deviation within. Now we want to go looking for measure of variability between the groups. So between or among the groups, the way we do that is we look at the squared deviation between the group means and the overall mean. So remember, x bar is when you lump everybody together, or in this case the mice, take the overall average. Now what we want to do is see how different the individual group means are compared to those. And then I want you to be thinking back to that applet once again. We're talking about there being an overall mean somewhere, and we're taking the difference between that. So if they were more spread out, it would mean that these differences that we're just looking at, let's get back to here, it would mean that these differences would be larger. Okay, so in a sense then it's a good measure of the variability between the groups because we're taking that difference, squaring it as we like to do in statistics and mathematics because that tends to work better. Now the right weight to give statistically here is the sample size for the particular group. So let's go ahead and compute that for our mice data. So we want the variability between the groups. And let's see, here we go. So 56 was our sample size. And then our original mean was, our first mean is 39.68. So 39.68. Now there will be some rounding here that I'm not going to worry about. I'll give you the overall result. But the overall mean that we could get, and I guess I should do it for you so that you believe me, we could do mean of lifetime data equals mice, and let's just go ahead and run all these lines, and we get 38.797. So I'll keep the digits here for this first term. So 38.797. Okay, 38.797 squared. That's for group 1. Then group 2, we have so on with the sample size, and then the difference between the mean. So let's see, the difference between the mean, 32.69, and the overall, the group mean and the overall mean, and then square it, and then we'd add those up. But let me skip to giving you the last term, which was 56 was the weight. And then the group mean for the last group was 42.88. So 42.88 minus the 38.797 squared, and those all add up to being about 12,734 roughly. You can check that. But that's the sum of the total variability between the groups. Okay. The degrees of freedom is just one less than the number of groups. So instead of n minus 1, it's k minus 1. So 6 minus 1 is 5. So now if there's no difference under the null hypothesis, whether you're measuring between or within, the variability you're measuring should be the same. It should be the overall kind of variance or standard deviation. So we're going to take this value and divide by its corresponding degrees of freedom to get our mean square between the groups, right? So the sum of squares of the groups over the degrees of freedom of the groups. So here's what it looks like. We have 15, sorry, wrong one. Let's get it right. 12,734. And down below we have the 6 minus 1 or 5, and then we ended up with 2546.8. 2546.8. So that's a lot, right? Mean square group versus what was it for with error was 44.6. So those are supposed to be similar if there's no difference. So wow, that seems pretty crazy. So the F statistic says, well, let's look at that ratio. It's the ratio of the mean square between to the mean square within. So the MSG, Madison Square Garden, over MSE. So let's put in our numbers. So we had 46.8. All right, is that what we just had? Yep. And then down below we have 44.6. And our ratio turns out to be 57.1. Well, that sounds like a very big number. For certain combinations, this can be thought of as a t-squared, but, you know, t-values that we've looked at for, say, 0.05 significance have been on the order of 2 to 2.5, maybe close to 3. Think about squaring that, maybe get as big as 9 or so. So for a t-squared to be 57 sounds pretty huge. Now let's go over to R and take a look at what how we'd work with that and the p-value. Now I've flagged that the function that we're going to use is XPF, and specifically XPF, you put a number that you're interested in, then you'd put DF1 equals and DF2 equals. So so what we're looking here, this is the numerator, and then the second is the denominator. All right, and that's what we're going to plug in. So in this case, what we're going to do, it's going to have to do with the XPF of 57.10. Now, if it were Day of Gracious Living, we might be more interested in SPF if we were out at the beach, but that's not the case here. Sorry, dad humor applies perhaps. DF1 equals, so our degrees of freedom was 5 for the top. And the n minus k, we already saw, was 343. So that's going to be the idea. In fact, we'll be looking at the upper tail, so there'll be a 1 minus it. All right, so come on, let's go over to R. Here we are at R, and let's get to the right version of this. I've got too many windows now, but I think I'm where I want to be. So we have Well, we want let's do something where we can see a picture first. So let's take XPF of 57.10, and let's see, if I hit tab, I get the prompt. DF1 is 5 and DF2 is 343. 343. And let's see if we get something here. So we get something. It has a skewed distribution. Now let's think about this. Don't worry about the warnings. What if I run that again? I don't get the warnings again. Right. Okay. Yeah, I have to think about why that warning's coming up. I haven't pinpointed what's going on there, but these numbers and picture is fine. Okay, so it's never going to be negative. Why? Because we're taking the ratio of variances that are always going to be positive. Large is going to mean there's more variability between than within. So we're going to be looking at the probability of being as extreme or more extreme in the right-hand tail. We're never going to be looking at the left-hand tail as evidence against the null. That's important to know. Extreme in terms of the p-value is always going to be the probability at or beyond. Now, we at 40 something, what was our value here? For our F statistic was 57.1. Well, we're way off the charts here. If you want to see what this looks like, I'll just pick a value like 2.5 just to show you. If we didn't have such an extreme value, we might put something like this in there, and then we'd see the probability at or beyond would be it's just off the edge, 0.031. If you wanted, you could do the 1 minus as we did before. What did I hit? Oh, I have an X there. 1 minus, and then we get the 0.030 out directly. Okay, so that was just made up data. The relevant picture for our case is the one like this. The probability to the left is 1, so to the right is 0. If you wanted to get it directly, you'd put 1 minus, and that would give you the probability in the right-hand tail. But suffice it to say, we can see by this picture that 57 is way out here. Very strong evidence of a difference overall. So the diet is certainly seeming to be related to the longevity of these poor mice. So let's take a look. So the p-value that we would get is approximately 0. So the p-value is approximately 0. We have strong evidence that something's going on, that there's a difference among them. So I went ahead and I worked out the results for you. So that's really where I want you to be at this point in your understanding. You're going to do some work in the warm-ups to fix some of the ideas with respect to these calculations. And in the reading, you'll see more examples of ways in which the data are laid out. And I will show you one other thing, and that's the LM command before we go. So let's take a look there. Okay, so let's go ahead and just use LM and see how we're going to do that. And here's an example we can open up. Okay, so the LM command shows up in the examples that I've given you here. Let me just move down a little bit. This was the ants experiment. So we want to copy this example here. So we'll call it mice.mod1. Let's see, do I have that in my commands here already? Maybe I do. Let me close a window or two here. All right. Well, I think I actually do have that in here already. All right, yes, I do. So here it is, mice.mod1. So we run the quantitative against the group or categorical variable. We get the ANOVA. It's not exactly perhaps the value that I got for the F, but it's very close. It's just due to rounding if there's a difference. This is the ANOVA table, a common way to format the results. The diet is representing our groups row. The residual is our within row. So the groups are between variability, the within variability. You can think of it that way. The residuals are the within variability. We get the ratio. The ANOVA, right? Oh, I'm sorry, that's what we're looking at here. The 44.6, the square root of that is going to be our standard deviation, our kind of pooled standard deviation that will be important when we look at confidence intervals for differences in means. But I think I'm going to stop here because this last section is what we're going to be talking about on our next lesson for 8.2. All right, so thanks for listening, and let me know if you run into any problems or difficulties with this, and I will see you next time. Take care.